Okay, so what we talked about yesterday is potential temperature. Okay, we're just writing pot temp for understanding. So why it is important? First of all, it's a conserved quantity. And what do you mean by conserved quantity? I think we have tried hard to understand that why it is conserved, why we are talking this, or why we are stating this as a conserved quantity. Secondly, to understand or I think to understand is a better way to write, to understand the stability in a better way, right? So to understand the stability. So what we haven't checked is the formulation perspective of this, because there's a quantity. Obviously, there's a quantity, and there should be some sort of formulation, some sort of formula to calculate. Otherwise, how will we quantify this? So for that, we will not. This videos are not meant to go with the formula, go with the mathematics, but rather to understand the concept. So, but still, formula is very much important for our understanding at some point as well. So in that case, if you are going this as the potential temperature, so consider this. Somehow this goes down. So theta equals to potential temperature. Okay. And then theta, how we will write it or how we will calculate it, what is the formula as such, is P by TP, if I'm not wrong, it is P naught by P. What is P naught and what is P, I will tell you later, by Cp. So if you can remember, during the definition, when we are talking about this potential temperature, we usually talk about some terms like, first of all, one is adiabatically. So we are transferring or we are moving, we want to move any parcel adiabatically, right? So that is one point. Second point is adiabatically from one pressure level to reference pressure level. So if we have atmosphere like this and we want to calculate the potential temperature over 600 hectopascal, what we need to do is we need an air parcel, okay, and we need to bring it down to a certain reference pressure level, that is 1000 hectopascal for the timing. So we need to do that. So we need an air parcel first of all, that we need to move from certain pressure level to certain references. This is the certain pressure level to certain reference pressure level. So this is for us is P0 and this is for us is P. So as you can see, P0 by P, okay. And then what we have is, obviously this air parcel has certain temperature itself within it. So this is the internal quality, okay, because of the internal energy, but because of any some sort of reason, it has some temperature within it. So that will be T for us, okay, that will be T for us. And then what we have with us is so this is another quality of the air mass. So air mass must have, so this is a gas constant. We will not go into detail. If we try to define what is gas constant, it will take a long time. So just we can say, so this is inherent property of the fluid. What is the fluid? Is air. So what we have with us is R and Cp. So this I can call inherent property of the fluid, and for us, what is the fluid? Fluid is air, right? Air parcel air. So it has some property, and on that basis this just comes as constant 0.238 or something like that, but I'm not sure, I'm telling you. So this is what we have with us. So how we can calculate theta from its inherent temperature must have at that level. So at 600 level, what is the inherent temperature? Is T. So again I'm telling you, so we will calculate this. So if this is atmosphere and this is 1000 hectopascal for us, and we want to calculate potential temperature at 600 hectopascal. Okay, so what we need a air parcel first of all. So this is a air parcel. Okay, so this is an air parcel. I'm sorry. So this is an air parcel. Okay, and now what we need to do is to bring this down 1000 hectopascals theoretically. Okay. This is not working. Okay, so theoretically we need to bring this down. Then what we have with us is obviously it has an inherent temperature T, and the constant for that air parcel is I by Cp. One is gas constant and one is heat capacity. Okay, so that we can calculate theta. And if we look into this, so this will be for theta at 600 hectopascal. So for theta, to calculate theta at 600 hectopascal, I will write like this. So first we need to understand the temperature at 600 hectopascal, and then we have to calculate this P0 by P and R by Cp. So this is always constant for all kind of air parcel. So we just not consider this. We have this, and what we are doing is T600 10,000 by 600. Okay, so 10 by 6 times of T600. That we need to remember. T by 600 into this. So theta 600 will always be greater than T600. That's what we are trying to convey last day, and that is potential temperature will be always higher than its actual temperature. Okay, so this is one point, that its potential temperature will be always higher than its actual temperature. So how it will happen? So overall in the atmosphere, as we go up and up and up, so it will not look like this. So it will look like this. So if this is temperature, this is water. We have potential temperature over here, and we have height over here. So it will always goes like this. Okay, so it will increase as you go up. It will increase, and not decrease. So from this point of view, we just add another thing, and then we come to lapse rate. Another important thing is what if. So this is a kind of air parcel that we have talked about. Is there is no moisture within it. It's completely just let me add another page. Let me just add another page, and then I will talk about it again. Okay, we don't have any space over here. A little bit of space over here. Okay, so in most of the cases what we are talking about is air parcel. So these are two type of air parcel. Okay, so this is considered it as considered is a dry, and considered is as moist. Moist means there are some sort of moisture. Okay, so one is dry for you and one air parcel is moist. Moist means just some water vapor is added within that air parcel, which is very normal. In normal case scenario, every time, most of the time, you have completely dry air, right? So this is nothing but a little bit of H2O in the form of water vapor. Okay, so suppose now if it goes up, okay, what happens? It will cool down, and whatever, it will cool down, right? Because our pressure decreases, so it will cool down. And if it goes up, what happens? It will also cool down, right? Why? Because of decrease in pressure. So decrease in pressure. So this is negative for us. So decrease in pressure. So just I think we need a fresh page. Yeah, let's go into a fresh page to understand this better. Okay, so there are two parcels for us. One is I'm typing just D and M. So dry and moist. Okay, so it has some temperature, that is T. Just writing TD, and it has some temperature TM. Okay, it goes up. Suppose this is 1000 again, this is 1000 hectopascal, sorry, this is 1000 hectopascal, and we try to bring it in 600 hectopascal. So we also bring this up. Okay, now what happens? Due to pressure decrease, so what happened in this region? We have a decrease in pressure, right? Decrease in pressure. Now, so for that reason, if we are doing every step again adiabatically, so just don't forget. So we are doing this step adiabatically again. So we are doing the stuff adiabatically. So if we are doing the stuff adiabatically, that means there will be no energy. So if we just bring the parcel over here, no energy will be within, no mass can come in or goes out. So nothing happens like that for this and for this too. So in these two cases it will not happen. So no kind of mass. So no, just writing, I don't know if you can see, no mass and energy transfer. So that is what adiabatically means. So if we do that, okay, and then obviously the temperature will, what happens? Temperature will decrease for both. So this is we are considering as dT, and the temperature over there as TD 600 and TM 600. Okay, so this is the case, and TD 600 will be always less than TD, understood, because it will goes up. We have less pressure over here, and that's the reason why the temperature will drop. In case of this also, the temperature should drop. We are not talking about, we are not referring that as potential temperature. We are just talking about as potential temperature. We are just talking it, or we are referring it as temperature only, not potential temperature. Please remember, because what we are telling is when it goes up, your temperature will decrease. We are mentioning that because that is some different way of telling. We are, in that case, what we are talking about, we are bringing the air particle from 600 hectopascal to 1000 hectopascal. In that case, the temperature will definitely increase because we increase the pressure. But here, our way of conveying the fact is different. What we are doing is we are just bringing up the parcel, bring the parcel in the upper atmosphere. Then what happens? Then obviously temperature will decrease for T dry and T moist both. So if that is the case, then okay, so both will decrease. So obviously it will be less than TD and it will be less than TM, right? But what happened within it? So in case if it will decrease, the TM what we are talking about is TM 600 will be less than TM. So if temperature decreases, if this is the air parcel for you, then whatever the water vapor will, it starts to condense, right? It starts to condense, so it will start to condense, and within this process what will we have with us is latent heat. So this is latent heat will be released. So it will release latent heat. But if it will release the latent heat, so this is the air parcel. Okay, so this is the air parcel, and it will latent heat it releases. But what we are talking about is adiabatic. Okay, so this is adiabatically happening. So obviously that heat will not go out. That will be within it. So that heat will be within the air parcel. So if we have within the air parcel we have more heat, then obviously temperature will be comparatively more. If we are comparing these two, one is as the dry and another one is as the moist, then if we make both this, bring this up, 600 hectopascal, then what it will do, it will release latent heat, and that latent heat cannot come out, okay, cannot come out, and it will become warmer in comparison to that. So warmer than D. D means the dry air gas. So it will become warmer, then it will take more time, and it will have to go higher for being stable. So this is so then from this concept, so overall from this concept, there is another term was coined, and that was equivalent. So we have initially potential temperature. Now what we have, if we have moisture in the air parcel, then that is known as equivalent potential temperature, or rather in short we can write it like this, theta E. So in that case, what we are talking about, or how the term can, how the definition can be stated, is that if we have a moist air parcel, so if we want to bring it to a certain reference level adiabatically, then the temperature we would attain is known as equivalent potential temperature. Okay, so we have a moist air parcel. First of all, we have to mention the moisture can be different. The amount of moisture it has is not something constant parameter. No, it's not a constant parameter. It can be different for different places, different for different air parcel. So the moist air parcel that should come, that should brought close to land, or brought to certain reference level adiabatically, then the temperature would attain is known as theta E, or equivalent potential temperature. Now the question is, for a certain level, so for example, if we are talking about 600 hectopascal, so what will be more? Potential temperature will be more, or equivalent potential temperature will be more? For our primary concern, what we understand is our potential temperature will be, so if we are talking about on a subtle level, so okay, just in reverse way if you are thinking about it, so I'm not sure in reverse way if you can think of it. Okay. So in reverse way it is tough to think about it, because if it is 600 hectopascal for example, so you have a dry and you have a moist air parcel. We want to bring this both in the reference level, that is 1000 hectopascal. Now if we try to want to bring both that in, now the question is, the temperature is higher over here. Temperature is higher over here, or I don't think it's higher. I mean, okay, we have some sort of moisture is there, or if it is saturated, things will be different, and I'm not sure, but okay. So that is quite a bit different concept, or different way of thinking. How to there are a lot of I mean, what is the condition of that air parcel is very much important to understand. If we have water, condensed water, and we're not talking about water vapor, so if we have water over there, then I think it's not working again. Okay, so if we have water within it, so instead of water vapor, if we have water within it, then that will be yes, something to understand better, or it may not be a confusing. because if we have water over there, okay, in that air parcel, we're not talking about water vapor. So if you bring this down over a certain reference pressure level, so okay, this will, due to pressure change, this temperature will change and the theta will be something. Okay, so as you know that theta 600 will be higher than theta 1000 or theta 800 or something like that, theta 800, theta 1000, anything, or is comparatively higher because due to the pressure change, whatever, it's not a proper way to write it, I'm sorry. So if you just bring this down, due to the pressure change, the temperature will be, whatever the temperature will attain is the potential temperature. In case of this, whatever the temperature it will attain is known as the equivalent potential temperature. In that case, if you have water, then obviously that water will try to as it goes down, obviously, so if this is the case, so just talking about the moist air parcel, as it goes down, so what will happen, this become positive. So if this become positive, it will impact the temperature, or obviously in high pressure, within the energy, in terms of energy, so in terms of energy, in terms of temperature, it will increase, right? If you bring this parcel down over here, so this is 600 and this is 1000. If you bring this down, this will increase, but we have water within it. Okay, so just remember we have water within it. So if that water will take that energy and it become to water vapor, then obviously our energy become decreased in comparison. So energy decrease, or heat or energy, whatever way we want to write it down, so heat or energy, both of them decrease. So if that decrease, then obviously our temperature will be less. If temperature will be less, then theta u will also drops, right? So this is the case. So this is the way of thinking, or way of understanding stuff. Now I think we have time to go into our next one, that is the lapse rate. So before going to lapse rate, I think we have some other plans, and that is from theta. So we are talking about so we usually talk about so far is about theta and how theta changes. Okay, so what we understood over here from so far, that how theta changes along the atmosphere. So if this is the atmosphere, and this is again just in a conventional way I'm telling everything. So this is I don't know why suddenly it doesn't work. Okay, so this is 1000 hectopascal. So this is 1000 hectopascal. Okay, and this is 600 hectopascal. Okay, so okay, so what we understood is as we goes up, our theta is increasing. Okay, so this is not the graph. So theta increases as it goes up. So it should look like so if this is theta over there and h or height over there, it will goes up. So in normal condition, that means the theta in 600 hectopascal. So theta in 600 hectopascal will be always greater than theta in 800 hectopascal. That we understood so far. So in normal conditions, so it is very convenient to say that, so the difference between theta 600, and theta 800 may be considered as d theta. Okay, so d theta by dz, and with height, okay, with increasing height, theta also increases. So this is the normal convention. D theta by dz should be greater than 0. That means it increases. Okay, it will increase up. So this is the condition for a stable atmosphere. So in stable atmosphere, this will happen. But in unstable atmosphere, it will reverse. Obviously, it will reverse in unstable atmosphere. So in unstable atmosphere, what it will happen? So in unstable atmosphere, first of all, if this is the condition for stable, you can think in another way. So if this is a condition for stable condition, unstable condition, obviously the equation will be like this. How? When we usually call unstable. Unstable means in that case, why it is stable? First of all, why it is stable? Look, as I initially told, that potential temperature is very useful or a very comfortable way for understanding instability, because we have so if this is just for example, this is 2 level. I'm not talking about some thousand or anything. So this is H1 and this is H2. Obviously H1 in terms of height, H1 is greater than H2. So the temperature over here, or the potential temperature over here is theta1, the potential temperature over here is theta2. So obviously theta1, I'm not this time okay. So basically theta1 is greater than theta2. That's what we have understood so far. Okay, so if anything we have over there, air parcel over there. So this is air parcel which have a temperature of theta1. There is the air parcel which have a temperature theta2. So we have something, some air parcel. So this is P1 air parcel 1. This is P2 air parcel 2. And P1 has a higher temperature than P2. That means it will be less denser, and buoyancy basis, or from the point of view of a buoyancy, from the point of view of a high temperature, it should be above P2. So P1 should be above P2, right? Because we have higher temperature, so we have higher temperature or higher potential temperature, because potential temperature is an easier way to understand that. Higher potential temperature, and that makes it less dense. So this is very good to understand that, okay, that is very comfortable way that, okay, it should be above P2. So initially what happens? Initially we have P2 bottom, P1 up, and after calculating all this, what we have with us is again P1 up, P2 just below them. So they are stable. Wherever they are comfortable in their position. They don't want to change it. So that is the stable condition or stable position. But if d theta by dz, so as we told, d theta by dz is less than 0. That means what? That means we have theta1. Again, we have we have space over here. Okay, so we can do the stuff over here. Okay, so the same thing. We have two. One is P2. We are passing. One is P1. It is staying over H1. It is staying over H2. It has pressure theta1. It has pressure theta2. Temperature theta2. But what we are talking about is theta1 is initially what happens? Theta1 is greater than. This case theta1 is less than theta2. So it will obviously, then what will be for d theta? So initially here, what is d theta? What is d theta? That is theta1 minus theta2 by h1 minus h2. That is d theta. So this part should be positive. This is also positive. So ultimately everything becomes positive, and what becomes positive? D theta by dz. It becomes positive. So that means it is greater than 0. That means it is stable. Okay. Here what happens? Theta1 less than theta2. Then theta1 minus theta2 by h1 minus h2. So this becomes negative. This becomes positive. Ultimately what we have with us is negative, and what is that? Is d theta by dz. Okay, d theta by dz, they become less than 0 because they become negative. Now, from a from a conceptual perspective, so we have something. This is, as I mentioned, is P1, it is P2, and we have theta 1 for this, theta 2 for this. So if theta 1 less than theta 2, so that means what? It is denser. First of all, it is cold. First of all, it is colder. Not colder is not a word. Sorry. Cooler than theta 2, which makes it denser. As it dense, it will sinks down. If it is dense, it will sinks down. So it will not, not in its previous position. It will not want to stay in its previous position. It will just try to goes down. So that mixing, that will that will result in a mixing, and so this will result in mixing, or this is an unstable condition. When this happens, now in normal temperature and normal atmosphere, when this happens, usually call it when we have good amount of convection. When we have good amount of convection, when we have when we have when we have in a certain place we have a low pressure. Okay, in certain place we have low pressure region. So in that case, what happens? So in that case, we usually call it an unstable condition. So if we try to understand this mathematically from that formula, that will be easier for us. So what is the formula for this? So here we have, suppose this is 1000 hectopascal again. Okay, and this is 600 hectopascal or something like that. So low pressure means what? Low pressure in the below and high pressure in the up. Right? High pressure in the up. Now, if we go back into the normal definition or formula, then what we have is P0 by P R by Cp. Okay? Then what have with us? If we have low pressure over here, high pressure over there in the up, then P0 less than P, right? So this will be P0 by P less than 1, and if less than 1, this is a constant, then theta will be what? Theta by T is also less than 1. It is not less than equals to, but it is also less than 1. So theta will always less than T. So in that case, what happened? Theta over here will be less. Understood? Theta over there will always be less, and if that is the condition, that in normal, this is not present condition, that is unstable condition. In present, in normal condition, what happens? This will be more. This will be more than. It will be greater than T, or if we are considering 2 particularly, so theta 600 will be greater than theta 800. But here the things are different. Theta 600 is less than theta 800, and that causes unstable condition. So from potential temperature, how stable condition and unstable conditions are clarified. But this is the way of concept, way to understand the concept rather. Maybe in some day we will also talk about those monostatic, not monostatic, that is dry adiabatic lab state, adiabatic lab state, and lab state. All those concepts we will also try someday.